Jai Hind all of you. My name is Dr. Nitya Sharma. I am Assistant Professor at Garg Engineering College. Today we are going to discuss the topic graphite and fullerene, which is in module 1, and obviously it is very important topic as per the university syllabus. As for example, for each and every semester the question of graphite and fullerene is being asked, and it is more or less asked every semester. So either in 2 marks or 5 marks and even in 10 marks for the fullerene also. So it is obviously very important topic. We cannot change it. Now when going to the graphite first, this is graphite. When we are talking about the graphite, how questions are being asked. Why graphite is good conductor of electricity, density of graphite is lower than diamond, explain. Why graphite can be used as lubricant, explain. These type of questions, reasoning questions are being asked for the 2 marks, and for the 5 marks it can be asked a wholesome question, that is structure, preparation, properties and application of the graphite. Now first we talk about the preparation of the graphite. For the graphite, it is heated with the anthracite or coke. The anthracite, which is the purest form of carbon, in which carbon percentage is maximum. So anthracite or coke is being taken and it is heated with the ferrous oxide, which is a reducing agent. So the reaction 2 takes place, which is silicon carbon plus carbon dioxide. Now this SiC is when heated, then it convert into graphite. Now we talk about the structure of the graphite. Graphite, it itself is very important and very specific molecule. Why it is specific? Because it is having a hexagonal net. It is having flat 2-dimensional sheet of the carbon, and which is regarded as fused system. It means there is collective hexagonal rings for the graphite, and these layers are held together, one layer to the another layer, one layer over the another layer, which is held together by the van der Waals forces. Carbon-carbon bond length between the sheets is 1.41 Armstrong and distance between the layers is 3.35 Armstrong. These are the salient features which are important for the structure of the graphite, and most important is hybridization. Hybridization in the graphite is sp2. When we talk about the carbon, then carbon itself, it is having atomic number 6. When we are talking about atomic number 6, it is 1s2, 2s2, 2px, 2py and 2pz0. Here there is no carbon. So when hybridization 2 takes place, one electron jump over here, and this hybridization, this S and this 2p hybridization matches with each other and form sp2 hybridization. Now this 4th valency remain vacant. This 4th valency, when we talk about this 4th valency, this is unbonded p orbital, this is unbonded p orbital. 1, 2 and 3 bonds are there, which are hybridized and which are forming the sigma bond. So overall it is forming a hexagonal ring with each other, and this kind of cyclohexane ring is formed. Upper p orbital and lower p orbital are free to with the help of delocalized electrons. Now when we talk about the structure of graphite, this is wholesome structure which we have to draw in the exam. Then it is having cyclohexane ring, and this cyclohexane ring are holding together with another sheet, this sheet and upper sheet, by the bond length of 3.4 Armstrong, and these are attached by van der Waals forces, which are very weak type of forces are there, and this is distance between 2 covalent bond is 1.42 Armstrong. So let us draw the structure, as it has been found that we generally found difficult to form structure of the graphite. So, for sake of easy how to draw graphite structure, I am just drawing it. Just make two layers, one over the another layer. These three bonds are of equal length. So these are here and this is the back bonds. These are again back. These are front bonds. So we will make this structure with the help of this carbon. And these are the back bonds. So we will attach them. And these are the bonds which are in front of the molecule. So we will attach these. And these are the two bonds which are also attached with each other, the back one and the front one. So this is how we can draw the structure. What we have to mention the distance between them, which is approximately 3.4, and this distance which is approximately 1.4 angstrom, and thus it is very much important. So this is the structure. Whenever the question about the graphite has been come, this structure must be there in your sheet, and which is important as per the exam. Now we talk about the types of graphite. When we are talking about the graphite, there are two types of graphite. One is referred as alpha graphite, another is referred as beta graphite. Only difference in these types of graphite is their arrangement. In case we say in alpha graphite there is AB type of arrangement is there. In case of beta graphite there is ABC type of arrangement is there. There is slight changes in the sheet, slight distortion in the sheet, and so one sheet is not exactly parallel to the another sheet. So this is types of graphite and how they can be interchanged to each other. They can be interchanged to each other when we just grind it. Grind is just crushing it finely. Then alpha graphite is converted into beta graphite, and when heating is done, then beta graphite is converted into alpha graphite. Now these are these specific important questions which are asked generally in the 2 marks question, and if you miss something then you will not get full marks even with the 2 marks. So what we have to write in case discuss the lubricant nature of the graphite. So you have to write the hybridization we have discussed, that with sp2 hybridization is there. The fourth valency is free fourth valency, and thus is result into slippery nature. That bonding in layer is weak, which is van der Waals forces. It form van der Waals forces. So this, because of this large interlayer distance, which is result into remarkable softness of graphite, and thus it can be used as lubricant. So there is wide spacing in this. So because of this wide spacing, this is density of graphite get lowered because of the large gap, and thus which makes this graphite very smooth material, and thus graphite is a very effective solid lubricant. It can withstand with the pressure for a larger variety, and thus it is very much important. Now the second part of the property, that is low density of graphite. Low density of graphite, when we are talking about the density of graphite, already we have discussed that because of this wide specifying, but when, which is very important. But when we are talking about the specific questions of the graphite for the 2 marks, then we have to write, start from the sp2 hybridization, 4th free valency, distance, interlayer distance between them, and thus which is making this graphite density lower, and which now this graphite can slide over one another, and which makes this graphite a smooth material, and because the density of graphite is very much lower than the diamond. Now the next property, this is conducting nature of the graphite. Obviously, all these properties are interrelated with only one thing, that is the 4th free valency of the carbon, which is attached with each other with the van der Waals forces. So, what are van der Waals forces? Van der Waals forces are those forces which are very weak, and thus electron can easily move here and there, so on, which are referred as delocalized electron. So, because electron can move because of this unhybridized p orbital, hybridization is sp2, the 4th valency of carbon is still free, and it is the electron can be moved easily, and so this delocalization in the unhybridized p orbital are free to move anywhere within the sheet, and so the electrons are no longer fixed. And what is conducting nature? Conducting nature is the movement of the electron in the sheet. The one thing has to be keep in the mind that electrons are delocalized. They can be moved here and there, but not from the one sheet to the another sheet. Means within one sheet, electrons can be moved, but with the another sheet, the electrons cannot be moved. So, other properties of graphite. One question may be asked, is it possible to convert graphite to the diamond or vice versa? Can we convert it? Yes or no? If it is, we can, then it will be so easy. We are having so much amount of graphite and we will convert it into diamond. But there is a small issue which cannot be very small. So, graphite is much more stable than the diamond, and the free energy of formation of the graphite is 1.9 kilojoule per mole. What is this free energy? What is this amount of energy is liberated when the graphite is formed, and so this which energy is already liberated from the formation of the graphite, so which makes this graphite very stable. Now thermodynamically it is favorable for the diamond to turn it into graphite, but they do not normally do so because there is high energy of activation is required. So although this is diamond, for the diamond we can turn into graphite because obviously graphite is much more stable than the diamond. So we can easily guess we can convert graphite to the diamond. Though we cannot convert graphite to the diamond, but diamond can be easily converted into graphite, is it? But it is not. Why it is not? Because initially high energy of activation is required, which makes this reaction unfeasible, and the reverse process is again not possible, and the high energy conditions and which is required to the synthesis diamond is 1600 centigrade and pressure is 50,000 to 69,000 atmospheric pressure. So, property and uses, other properties, what are the different other properties? It can, because of high melting point, it is again this high melting point also withstand with the formation of high which can be work as lubricating material, as a solid lubricant, it can withstand with the pressure also, which makes it lubricant, and high melting point is also there, and so it is also used as a refracting material for the lining of electric furnace. Now, it is insoluble in the water as well as organic solvent. In generally, which are general materials are there, which are either soluble in water or organic solvent, but graphite, it is insoluble in the both. Now, what are the applications? Why applications are important? The material which we have having no use is not important. Why? Because everything has to be its use. Otherwise, why should we go the indication of there? Why we get pen for the learning graphite or even fullerene or even anything? So, why this is so? Just because a graphite we find a lot of application with the graphite. The first one which we very commonly use is pencil, solid lubricant, because of low fraction of coefficient is there, refractive material for the lining, electric furnace is there, electrodes, it can be used as electrodes because it is conducting in nature, and it is not metalling, which makes this graphite a very usable thing for the electrode purpose. It can be used as the batteries, it can be used in the solar panels because it withstands with the temperature also. Carbon brushes as moderator rods in the nuclear reactor because there are gaps in the two sheets of the graphite because of van der Waals forces. So, that bombardment of alpha particle, beta particle, gamma particles which are continuously being taken place in the nuclear reactors are supposed to be absorbed by the graphite, and so it is used to control the speed of the nuclear reaction, which is referred as moderator rods. Now, it can be used in the brakes, which it is used in the graphene sheets. What are graphene sheets? Graphene sheets are single layer sheets of the graphite are referred as graphene sheets. Graphene sheets can withstand with the temperature also, and so on. So, in nanotechnology, graphene sheets are much more useful nowadays. So, it is being used, and synthesis of carbon nanomaterial. Once these graphene sheets are used, they can be rolled up, they can be balled to make the different material, and so it can be used in the formation of different nanomaterials. I hope till now you have got the complete information about the graphite. Other allotropes of carbon we are talking about now is fullerene. What are fullerene? What we are talking about the fullerene, when it comes to the fullerene is having a very interesting history about this. This is referred as first nanomaterial of the subject, first nanomaterial which completely changes the technology, which completely changes the scenario. These days we are just talking about the lesser and lesser memory space, and which is all due to nanomaterials. When we talk about the nanomaterial, then fullerene is the first nanomaterial. Fullerene, questions may be asked, Generally, they are asked for the 10 marks each semester without any gap, which makes this Fullerene very important in terms of the exam. So, this is what are Fullerene? Discuss preparation, structure, properties and application. Discuss another terms which is given as truncated isohedron geometry, allotrope of carbon which is having truncated isohedron geometry, that is referred as Fullerene. So, both questions are having answered the same. We are going to discuss it now. It was discovered by Croto, H.W. Croto, Robert F. Curl and Smelly in 1985, and it is new allotrope of carbon which are arranged in a closed shells. How it is being discovered, that is also a story. It is discovered during the experiment of laser vaporization of graphite rod in high vacuum chamber. This is how it is being done. That this is a inert gas chamber. Inert gas chamber, generally neon, argon or krypton. What we have, any can be taken. These are the graphite rods which are used as a conductor as well as the precursor for the substance. And gas flow is there. It is the complete system is connected with the power supply, and when the power supply is on, then arc plasma is formed and which result into this one black shooty dust. This is red, so but it is black actually because it is all carbon. So when this carbon, this shooty dust was filtered, gone through the chromatographic technique. What is chromatographic technique? Chromatographics are these kind of glass pipes from which in this silicon is filled, that white color silica powder is filled, then the black shooty dust was kept here. And over to it, different kind of solvents are used as per polarity, and so we get the different bands of the substance. If my shooty dust is comprises of 2 or 3 or 4 types of powders or 4 types of compound, then here we will get 4 bands. Step by step, when as we go the solvent here, we will collect the details here, we will collect the one part, another part here, and thus it can be go through the what we are having in the solution. So this is how one preparation is done, one thing is being identified, and after this identification, this allotrope which is known as Buckminster Fullerene in honor of architect. So this is again a story how this is named after architect Buckminster Fullerene, which is having no relation with the chemistry or the discovery of Fullerene. So what happened actually, that Croto and Smelly has got C60 carbon, and what he found? He found there is no corner carbon. When we referred as no carbon corner carbon, then how the structure is possible? Before the discovery of Fullerene, there is all carbons which are possible are either linear or aromatic, and if it is aromatic, it is like benzene or cyclohexane, but a huge amount of carbon which are attached together and which are having no corner carbon. So they are putting their heads together. The complete team was having a head together, and there is no result out how they are connected towards each other, and they go to the fair and they found a half football shaped gate in the Fullerene in that fair, and that is how they have got idea that this Fullerene is having a closed structure, this kind of structure, closed structure in which pentagons and hexagons rings are there. So structure, it is a cage like structure. Fullerene, though C60 was discovered first and it is most studied kind of the fullerene, but fullerene itself is not a compound, it is a class of compound. It is a class of compound which are having formula C60. In fact, it is started from the C20, C40, C60, C70, C78, C120 and so on. The two examples are also here which are having C60 and C68 type of fullerene. So, fullerene itself is a closed cage-like structure which is hollow in itself and which are referred as fullerene. So, all carbons are on the surface, no inner carbon, all carbons are outer carbon, no corner carbon. So, the structure is isohedron and this isohedron structure is specified for the fullerene. Now, structure of the fullerene, it is a very important part of the fullerene because all the properties of the fullerene are because of this structures also. So, diameter is 0.7 nanometers, 30 carbon double bond are there. These carbon double bond length is 1.38, single bond carbon length is 1.45, 20 hexagons are there, 12 pentagons are there, 32 faces are there. These are the double bond which is having which are connected with the that cyclohexane ring which is bond length 1.38 angstrom. Pentagons which are having carbon single bond is 1.45 angstrom. Total number of pentagons are 12, hexagons are 20 and vertices corners are 60. So, for the specifically Buckminster fullerene C60 carbon, when we are talking about, the total number of corners will be 60. So, what is the restriction? Restriction, no two pentagons touch with each other. So, there is one more major issue of drawing fullerene in the exam. So, what we are going to have is structure of fullerene, how to draw structure of fullerene. So, first make a pentagon. Try to make a pentagon with all equal side. If you are having all equal side, then there will be no issue. Just place a straight line from the pentagon. All equal lines from the pentagons. Then a parallel line from this pentagon just exactly equal to this. Now, attach this parallel line to this. Now we are having a center pentagon and hexagonal 1, 2, 3, 4, 5 hexagons which are attached with the pentagons. So these are hexagons. Let me label it. These are hexagons. Now from these hexagons, there will be again attached. What we are saying? No two pentagons are attached with each other, though these hexagons are attached with each other. So how the this pentagons will be attached to this? This pentagons are attached to this like this. Now what else? What is remaining part? Now this is slightly the next part is this is not buckyball structure. What else is required is the hexagon which are attached to these pentagons. And where are the double bonds? Double bonds in the ring which is which is hexagon. So 1, 2, 3 double bonds are here. This is not, there will be alternate double bond. So this double bond is there. And so this will be next 1, 2, 3. Then again this way you can draw the double bond. What are the important part of the fullerene? Fullerene, this distance, double bond distance is 1.35. Single bond distance 38 Armstrong rather. This is 1.45 Armstrong. Carbon-carbon single bond which is slightly larger. Double bond is 1.38. Now 30 total carbon-carbon double bond, total number of 32 faces, 60 vertices, 12 pentagons, and hexagons. Now, when we are talking about this complete structure, one more thing which has to be written here, that is hybridization is again sp2 here. So, this is fullerene. Now, we talk about the properties. Properties, it is soluble in water, cannot conduct electricity. Obviously, the complete closed structure is there. Itself, it do not conduct electricity unlike graphite. So, it is soft and slippery because it is having ball-like structure. It is brittle, low melting point, and it forms deep magenta solution when dissolved in the benzene. It is tough and thermally stable. It exists as a discrete molecule. It can be compressed up to 30% of its volume without destroying the carbon cage. Then, when we are talking about the physical buckyball structure, it can withstand, it can resist the high pressure and which can bounce back to the original shape over the 3000 atmosphere. Other properties. So, when we talking about the chemical properties, then the magnetic fullerene can be obtained, though it is itself is not any electrical conductivity or magnetic property, but when mixed with the organic compound, this fullerene is converted into magnetic property. Now, the fluorinated fullerene C60, when each carbon is having a double bond here. Each carbon is having a double bond with either within the benzene ring, that hexane ring, rather the right thing which I have to say, that when that double bond is open and fluorinated, which is referred as fluorinated fullerene, it is referred as Teflon ball. Now, which is having we talk about the C60, it is mustard yellow and look brown and black as its thickness increases. If the thickness increases, the color is slightly changes. Then carbon 60, which is having tendency to avoid the double bond, electron delocalization is poor, but aromatic characteristic is absent, and thus it undergoes with the electrophilic addition, not the nucleophilic addition. Properties, other properties, when it is mixed with the alkali metals, specifically rubidium, cesium, sodium even, potassium and lithium, this is FCC kind of structure. FCC kind of structure, face-centered cubic structure is there. Face cavity at all the faces, one atom on the corner and another atom on the faces is there. This is referred as face-centered cubic structure. So, this is how fullerene arrange themselves in a face-centered cubic structure, and thus in interstitial spaces there is possibility for intercalation of the metal, which is generally small metals. First, alkali metals are 1s metals, and thus they are having a very small size, and thus it can be used for the superconductors. So, which are the applications? It can be used as superconductors with the intercalation method, as we have discussed earlier. Superconductor with the alkali metals, take parts in catalytic process, used as therapeutic agent due to stability. It can be used as potential inhibitor to HIV. Some derivatives of fullerene which are found with the help of solvent, and which are also soluble in the water, which are found potential inhibition with the HIV. So, it can be cured with the for the HIV. Trapping smaller size ion in the solution of water, so that FCC structure, which is having capability of absorbing some small molecules within the interstitial spaces, so it can be used for the trapping purpose. It can be used as lubricant due to spherical structure. The ball acts as molecular ball bearing. It is used as soft ferromagnet with the help of, though itself it is not a magnetic, but with the help of TDAE, that is tetrakis dimethyl aminoethylene. With the help of this can be used as soft ferromagnet. Now, this is non-linear optical device. Because how this can be used as non-linear optical device, because it is having all even faces, so it can be used as molecular periscope, and thus it can be used in non-linear optical device, and it can be used in electronic, micro electronic devices, and so on. So, this is all about graphite and fullerene, which are the allotropes of carbon, and these days the study of fullerene and graphite is much more extensively being done, and it may be useful for further purpose, as different applications are there for the graphite and fullerene itself. The specificity of a person or a material is an application only, not what it is. Until it is not useful, nobody will take care of this. With these words, I hope I can complete this topic, graphite and fullerene. go through the video and find out the important points for the graphite and fullerene. Thank you.